All right, as wonderful as the law of sines is, it's not quite enough to solve every single triangle situation that we might encounter. For example, if we have, say, a triangle and we're given, say, an angle, let's call this, say, 32 degrees, and let's say this is a length of 8 and a length of 13. The law of sines is not enough to solve this triangle, because notice that we do not have an angle and opposite side pair. We are given an angle here, but we are not given its opposite side. And we don't have enough angles to find any other angles using the 180-degree trick. Of course, you need 2 out of 3 for that. So law of sines really falls apart here. And one more situation where the law of sines falls apart would be if you were given, say, a triangle with 3 sides but no angles. Now we don't have any angles, so of course we don't have any angle and opposite side pairs. And in order to use a law of sines, which is a wonderful rule, you do need to have an angle and opposite side pair given in the problem. So, okay, so we're missing something, and that's the law of cosines. The law of cosines is exactly what we need to fill in that last gap of information. So between the law of cosines and the law of sines, we will be able to solve every triangle we come across, provided there's enough given information to begin with. All right, so let's try and uncover this new law of cosines. So just like we did with the law of sines, let's suppose we have a generic triangle ABC, and let's draw an altitude here, and we'll call it H, as we did before. Now we have 2 independent right triangles, and let's use a little bit of trigonometry from right triangles to establish some basic facts here. But before we do that, let's quickly label some sides here. So this will be side A, this is side C, and in fact, we know this whole bottom here is called B, but let's label just this segment right here as X, and let's label this segment over here as B minus X, which is all of B minus X. Okay, now let's look at our right triangles and extract some trigonometric information. So let's note that cosine of capital A is, of course, adjacent over hypotenuse, so that would be X over C. And therefore, X is equal to C times cosine of capital A. All right. Now looking at the other triangle, we can see by the Pythagorean theorem that the hypotenuse, which is in this case A squared, is equal to H squared plus B minus X squared. All right, so let's work with this a little bit. Let's FOIL out the B minus X squared, which will be B squared minus 2BX plus X squared. Well, here we have an H squared and an X squared. And let's note also by the Pythagorean theorem that H squared plus X squared is equal to C squared, which means that we can replace H squared and X squared in our formula here with just C squared. So we are now at A squared is equal to B squared plus C squared minus 2BX. Okay, but we established very early on here that X was equal to C times cosine of A, which means that A squared is B squared plus C squared minus 2 times B, and X is C cosine of A. And that is the law of cosines. Again, notice we have arrived at a formula that does not involve X and it does not involve H. So it just uses the elements of the triangle itself, A, B, and C, and capital A here. Okay, and just like the law of sines, you can permute the a, b's, and c's around. So there are 3 different ways of writing the law of cosines. All right, so now you can't just put any letter anywhere here. Notice that at any given time, one of the lowercase letters, so a side length, is isolated on the left-hand side. Okay, so if this letter out here is an A, then this letter over here is a capital A, and the other ones in the middle are B's and C's. So note that when you do have capital C equaling 90 degrees, in which case you have a right triangle, then this last line of the law of cosines is actually just the following. Cosine of 90. And of course, we know that cosine of 90 evaluates to 0, which being multiplied by 2ab eliminates it, and we simply get the Pythagorean theorem. So the law of cosines can be thought of as a generalization of the Pythagorean theorem. So this tells more of the story. All right, let's look at some examples. All right, here we have the description of a triangle that we need to solve. And we will make an attempt to draw this triangle, but again, I want to point out it's not strictly necessary. If you just write out a template for your final answer and you load it up with the given information, well, at a glance, you can see that the law of sines isn't going to work. We're going to need the law of cosines because we don't have an angle and opposite side pair known. We don't have an AA, a BB, or a CC pair already established. Okay, so let's look at this visually by trying to draw this triangle. So usually I put angle A at the bottom left, but this time I think I'll put angle B down here because that's the angle that's given. So an angle of 73 degrees is, well, it's about like that. So why don't we just decree that that is side A, and it's 28.2 feet. Which means that down here will be side C, which is 46.7 feet, and that's about 1.6 times longer than the other one. So maybe something like that. And internally we have angle B, which is 73.5 degrees. Now also, one nice thing about drawing the triangle is that you can convince yourself that there is only one triangle that can be determined by these descriptions. So there's only one way to finish drawing this triangle, and of course that would be connecting the last two ends here. So okay, this will be angle A, and this will be angle C, so they're appropriately opposite the sides that we labeled. Very good. All right, we're going to use the law of cosines, which is really well suited when you have two sides and the included angle between them, as we do right here. So we should use the law of cosines to find little b. That shall be the isolated term. So we'll use the version of the law of cosines with little b isolated, and that means that we need an a here and a c here, minus 2a again, c again, times cosine of capital B. And everything on the right of that equal sign we have. It was given to us. So it's really just a matter of doing the calculation. So I'm not going to write the feet in here because this line can get very long, as you're seeing, even without putting the units in. Now, on an exam, I'd really like to see that written down, the calculation that you're using, okay? Not just the final answer. I need to see that statement that you're putting into your calculator so that you can earn partial credit. And one of the big reasons for that is, well, so I can see that you understand trigonometry, of course, but second of all, it's really easy to make a mistake entering this into your calculator. And if you don't show any intermediate work and you just sort of have an answer magically appear and it's wrong, well, you're going to basically get 0 credit. Show me the formula with the numbers plugged in, and if you make a mistake with the actual calculation, you'll still get most of the credit for the problem because I know you know trigonometry. You're demonstrating it. Okay, and also double check that you're in the right mode, in this case degree mode. So I get b squared equals 2228.07, and therefore b will be the square root of that, and I get 47.2024 feet, which of course we will write in our final answer here as 47.2 rounded. Okay, so now we're not done solving the triangle, but we are done using the law of cosines, because look at this. We now have an angle and opposite side pair, so we can finish solving the triangle using the law of sines. For instance, we can now find capital A using the law of sines, and in fact, once we have capital A, of course we're going to have capital C using the 180 degree trick. So let's quickly do that. So little a is 28.2 feet. And capital B was given to be 73.5 degrees, divided by little b, which we calculated to be 47.2024 feet. And of course the feet cancel, giving us a unitless ratio. So in my calculation, I have sine of A arriving at 0.572825, and we are just going to take the inverse sine of that to obtain A. So I get that A is 34.9475 degrees. Okay. And now we can find capital C simply by going 180 minus 73.5 minus 34.9475. And I get capital C is 71.5525, which is 71.6 degrees. And there we are. That triangle is solved.
Yeah, baby.
All right, here's another situation where we need to use the law of cosines. If we have 3 sides to a triangle and no angles given, and if we had a single angle given, let me just throw in an angle here. Let's say this is 61 degrees. Then the moment we've got an angle, we have an angle and opposite side pair, and you don't need the law of cosines at all, right? Law of sines would finish this, and it's a lot easier to carry out than the law of cosines. Okay, but we don't have an angle and opposite side pair given, and we want to find that theta. Okay, so we will use the law of cosines here with the side of 5 isolated, which involves the cosine of theta. So in other words, we could say 5 squared is equal to one of the other sides squared plus the other side squared minus 2 times the 7.7 times the 9.8 cosine of theta. So again, I want to stress that when you're using the law of cosines, the side that's isolated here, which is the 5, is the opposite to the angle that's in the cosine, right? They're opposite side and angle in the triangle, and of course they're opposite ends of the formula here. The other 2 sides in the formula are just the other 2 sides. They're adjacent to that angle, theta. Very good. We should do this calculation. This is one of the most common places for a calculation to go wrong. You must respect the order of operations, so I recommend doing this in several pieces. Remember, we're after cosine of theta, So that'll be the last thing we get isolated. So we should work out that in a single calculation. Okay, 2 times 7.7 times 9.8, I get 150.92. And that's the coefficient of cosine theta. Okay, we should also do that in a calculation. 7.7 squared plus 9.8 squared, I get 155.33. Okay, and then we're subtracting the 150.92 cosine theta. And then we should, of course, also do this calculation, which we can see is 25.0 without a calculator, of course. All right, so now let's subtract that term. And we're going to get 25 minus 155.33, which is negative 130.33, is equal to negative 150.92 times cosine of theta. Now, let's divide both sides by that coefficient, which will, of course, cancel the negatives. So I get 0.86357. And at this point, you can now use the inverse cosine function on that ratio. So I get 30.2802 degrees. Okay, so rounding it to the precision in the problem, we'll go with 30. So it's ambiguous whether 30 is one or two significant figures. In this case, it's two significant figures, and I'll just emphasize that by putting the little period right there. Okay, so here we have two boats leaving a harbor, traveling on different directions, and after a while, one of them's gone a certain distance and the other one's gone a certain distance, and we want to know in that moment how far apart the two boats are. It's a classic situation. Perhaps you got on one boat intending to get on the other, and a couple hours into the trip realized your mistake, and now you have to swim, and you just want to know exactly how far to swim. Well, it's a good thing you're enrolled in trigonometry then. So let's see. Draw a picture describing the situation. So let's make our harbor right here. And let's suppose that one boat went 62 kilometers this way, and making an angle of 82 degrees with that, which is almost a right angle. The other one went 79.4 kilometers. Okay, so we're just asking this question, well, what's the distance between the two boats? We can call it x, for example. All right, well, again, think of it like just solving a triangle problem, but you don't have to solve the whole thing. Usually in word problems, you just need one or two different measures for whatever the situation's asking. And here we want that particular length. So given that we do not have an angle and opposite side pair, well, we're going to have to use a law of cosines to figure it out. Big surprise. Let's do that. So of course we can see through the law of cosines that x squared will be equal to 62.5 squared plus 79.4 squared, it's just the other two sides, minus 2 times 62.5, 79.4, cosine of 82 degrees 20 minutes. Okay, so let's just do that big calculation. I get that x squared is 8,886.52 square kilometers, and taking the square root of both sides, I get that x is 94.2683, and answering the question using the precision given in the original measurements, we will say that the two boats are 94.3 kilometers apart. So, yeah, no problem. You can swim that.